Hello everyone, welcome back. In this video, we're going to talk about how to find the distance from a point in three-dimensional space to a line in three-dimensional space. Being able to solve a problem like this has lots of real-life applications. For instance, things like pipes, utility lines, and roads are often straight and can be represented by lines. And if we want to figure out how far an object is from something like a road, an industrial pipe, or a utility line, being able to do this process can help us solve such a problem. So I want to go ahead and state the formula we use for finding the distance between a point and a line. We'll talk about where this formula comes from and then do an example using our formula and actually finding the distance from a point to a line. And so we're going to let L be a line in three-dimensional space passing through some known point P, and our line is going to have a direction vector denoted by V. So M is going to represent some other point not on our line. That's the point we're trying to find the distance to. Then the distance from this point M to our line L is given by D, where D is equal to the magnitude of the cross product between the vector from P to M crossed with our direction vector of our line V, and we divide the magnitude of that cross product by the magnitude of our direction vector V. All right, so next let's go ahead and talk about where this formula actually comes from and derive it together. And so to do this, we're going to start by drawing a picture of our situation to get a visualization. And so we have some line L in three-dimensional space, and maybe it looks something like this. What else do we know? We have some point M that is not on our line. So M is some point not on our line. Maybe it's way up there. We also know some point P that is on our line. Let's maybe say our point P is down here somewhere. And so we're trying to find the distance from our point to our line. And while there's lots of ways to go from our point to our line, and when we say we're finding the distance from our point to our line, what we mean is the shortest possible distance from our point to our line. And it should be pretty easy to see and believe that the shortest path from our line to our point is going to be going through a straight line that is going to be perpendicular or normal to our line L. And so the length of this line segment from our line L to our point of interest M is going to represent our unknown distance D, the distance from our line to our point in space. All right, so we do not know this point on our line L that connects M to our line in the shortest way possible, and we can actually solve this problem without ever finding that point at all. And the way we do it is actually pretty clever and uses one of the geometric interpretations of the magnitude of our cross product. And so let me go ahead and add a little bit more to our picture to see how all this is going to come about. And so we do know this point M, and we do know at least some point on our line P, but it is not that optimal point that is the shortest distance from our point M to our line. But what we can do is create a vector from the point P on our line to our point M that is not on our line that we are trying to find the distance to from our line. And so we're going to be creating a parallelogram here in order to take advantage of that nice geometric property of our cross product. One side of our parallelogram is going to be given by this vector from P to M, and the other side of our parallelogram is actually going to be given by the vector V that is the direction of our line. So let's go ahead and add that to our picture. Maybe our vector V looks something like this. Doesn't actually matter what size I make our direction vector V or if it points in a kind of the opposite direction. It all works out the same in the end. And so now it still might be kind of hard to see how a parallelogram is in this picture or how it's going to help us. Let me add a few more lines to help us visualize this parallelogram. So the kind of one side of our parallelogram is this vector V. The other side is the vector from P to M. So if I make a copy of this vector V and attach it to the point at M, that'll be another copy of our vector V up here, and then I create another copy of our vector from P to M, but place it right here. And so this is just a parallel vector to our vector V with a different starting point, now starting at M, and this is a vector that is parallel to our P to M vector with just a different starting point. But now we can see in our picture that we do in fact have this green parallelogram. And now that we can see the parallelogram in our picture, we're going to calculate its area in two different ways. The first way we're going to calculate the area of our parallelogram is using that geometric interpretation of the magnitude of our cross product. Remember, if we take the magnitude of the cross product between these two vectors, then we can interpret that as the area spanned between the parallelogram between our two vectors. So the area of our green parallelogram is going to be the magnitude of the cross product between our two vectors that make up the sides of our parallelogram. That is our vector from P to M crossed with our vector V. And the other way to calculate the area of a parallelogram that we'll be using is not one that we've learned recently, but one we learned way back in geometry. And that's that we can find the area of a parallelogram by taking the base of the parallelogram and multiplying it by its altitude or its height. But what is the base of the parallelogram that we have here in green? Well, it's the magnitude of our vector V. But what is the actual height measured from like the ground or from the vector V itself or our line L? Well, the height of our parallelogram is actually given by that distance D. So now we know the area of the parallelogram is equal to the magnitude of this cross product, but it's also equal to the magnitude of V times this unknown distance D that we are trying to calculate. So we can divide both sides by the magnitude of V and find that the distance between our line L and our point M is given by the magnitude of the cross product between the vector from P to M crossed with our direction vector V divided by the magnitude of our direction vector V. And that gives us the formula that we started with in the statement of our theorem over here. And we now know how to find the distance from a point to a line in three-dimensional space using vectors, cross products, and magnitudes. All right, everyone. So in this example, we're going to find the distance between the point M, which has coordinates of 0, 3, and 6, and the line with parametric equations given by x is equal to 1 minus t, y is equal to 1 plus 2t, and z is equal to 5 plus 3t. So in order to find the distance from our point to our line, we're going to use our distance formula over here. This says the distance from our point M to our line L is given by the magnitude of the cross product between the vector PM and V divided by the magnitude of our vector V. So V is our direction vector, and we can recover our direction vector from the direction numbers inside our set of parametric equations. Remember, our direction vector is just given by the coefficients in front of our parameter t in our x, y, and z equations. So our direction vector v is going to be the vector with components of -1, +2, and +3. That is one of the vectors we are going to need in our calculation. The other vector we are going to need is the vector that goes from a point on our line P to the point of interest M. We know our point of interest M is 0, 3, 6. However, we need a point P on our line to connect to our point M to create our vector PM. So technically, any point on our line will be able to accomplish this. However, it's going to be easiest if we just use that starting point. And so the starting point that our line goes through, or we can think of as our starting point, are just going to be given by the constants in our set of parametric equations. So we can use for our point P here, the point that goes through 1, 1, 5. All right, so now that we have a second point, a point that is on our line, we can create the vector that goes from the point on our line to our point M, or our point of interest. And so our ending point is M, 0, 3, 6, and our starting point is P, 1, 1, 5. So if we take the difference between the first coordinates, we're going to get 0 minus 1. That'll give us -1. If we take the difference between our second coordinates, we'll get 3 minus 1, which is 2. And the difference between our third coordinates will give us 6 minus 5, which is +1. And it doesn't matter if we actually found the vector from M to P or from P to M here and reversed everything. It's just going to cause a sign change somewhere along the way. But because we're taking the magnitude or absolute value of everything, it'll all work out and give us the same value in the very end. All right, so now we know the two vectors that are needed to compute our cross product. So that is our next step, to compute the cross products between our vector PM with our vector V. So I've gone ahead and set up our 3x3 determinant to help us evaluate our cross product here. So in that first row, we have our basis vectors I, j, and k. The next row is denoting the components of our first vector in our cross product Pm, and those components are -1, 2, and 1. And the third and final row in our cross product, or our 3x3 determinant here, they're just the components from our direction vector v, or the second vector in our cross product, and those values are -1, 2, and 3. All right, so I'm going to calculate this cross product relatively quickly using the difference between the right and left diagonals starting at I, j, and k, which I covered in an earlier video. So for the I component, looking at that right diagonal, we get 2 times 3, which is 6. And we have to subtract away from that the left diagonal that starts at I and loops back around. And that left diagonal will give us the product of 1 and 2. So our I component is going to be given by 6 minus 2, or 4 after we simplify. Next, let's go ahead and find our j components. Starting with the right diagonal, from j, we get 1 times -1. Then we have to subtract away from that -1 times 3. So we have to subtract away a -3. Now let's go ahead and finish this off by calculating the diagonals for k. So the right diagonal will give us -1 times 2, or -2. And we have to subtract away from that the left diagonal, which will also give us a -2. So if we take these differences and simplify the components for our cross product vector, it looks like we're going to get the vector with 4i as the first component. -1 plus 3 is +2. So +2j for that second component, and then -2 minus -2 is 0. So 0k for that third component, or we could just write it as 4i plus 2j. It's not necessary to write the 0k. So we've calculated the needed cross product for our distance formula, but we're not quite done yet. The last 2 steps are taking the magnitude of the vector we just found in our cross product and dividing that by the magnitude of our direction vector v. So remember, to find the magnitude of a vector, we take the square root of the sum of the squares of the components. So for our Pm cross v vector, those components were 4i, 2j, and 0k. So the magnitude of that vector is going to be the square root of 4 squared plus 2 squared plus 0 squared. Then we have to divide that by the magnitude of our v vector, which is going to look like the square root of -1 squared plus 2 squared plus 3 squared. So we've calculated the needed cross product for our distance formula, but we're not quite done yet. The last 2 steps are taking the magnitude of the vector we just found in our cross product and dividing that by the magnitude of our direction vector v. So remember, to find the magnitude of a vector, we take the square root of the sum of the squares of the components. So for our Pm cross v vector, those components were 4i, 2j, and 0k. So the magnitude of that vector is going to be the square root of 4 squared plus 2 squared plus 0 squared. Then we have to divide that by the magnitude of our v vector, which is going to look like the square root of -1 squared plus 2 squared plus 3 squared. All right, so in our numerator, we're going to get 16 plus 4, so that'll be the square root of 20. And that's going to be divided by 1 plus 4, so that's 5, plus 9, that's 14. So we get the square root of 20 divided by the square root of 14, and we can simplify that as the square root of 10 over 7, or we could rationalize the denominator and simplify it further. If we did take a moment to rationalize the denominator there, we could write it as the square root of 70 over 7. All right, so using our newly found formula, we were able to find the exact distance between this point 036 and our line described by these given parametric equations. We found that exact distance to be the square root of 70 over 7, or approximately 1.195.